In this video, we're going to be introduced to the Bohr model of the atom. So one of the questions that we were left with in the previous videos is that classical physics couldn't explain emission spectra of atoms. It wasn't understood why the light emitted by atoms only came in specific wavelengths, and why different atoms had different line spectra, why they had different emission spectra. And so one of the first successful ways to explain this was a model of the atom developed by Niels Bohr. And in this model, the electron was described as moving around the nucleus of the hydrogen atom in circular orbits, and only certain circular orbits were allowed. And one thing that the Bohr model got right is that the energy levels of the electron are what we call quantized. That is, only very specific energy levels are allowed, and this was related to how close the orbit was to the nucleus. And so the reason we only saw specific wavelengths of light being emitted is because the differences in energy between the different orbits was fixed. And so you got one color of light when you went from orbital number 5 down to orbital number 2, and you got a different color of light when you went from orbital 4 to orbital 2, for example. And so all of these different lines in the spectrum corresponded to different transitions between the different orbits. And so one way to think of the quantization in the energy levels of an electron in an atom is kind of like a ladder. So the rungs on the ladder are fixed, right? And so your foot can rest on a specific rung of the ladder, but there's no space for your foot here. And so these different energy levels are the different energy levels possible for the electron in the atom. And we numbered these energy levels by what we call a quantum number. And so the lowest energy orbit is given the value of n is equal to 1, and as we go up in energy, the quantum number for that energy level increases. So the main things that the Bohr model got right was that the idea that the energy levels of an electron in an atom are quantized. Only certain energy levels are allowed. And Bohr was also able to come up with an equation to correctly predict the energy levels in the hydrogen atom. And his equation is given here, where we just have a constant out in front. J is just the unit. This is the energy in joules. Z is the charge of the atom, the charge of the nucleus. And n is the quantum numbers that we introduced to on the last slide. And so you can see all of the energy levels are going to come out to be negative in this model. And I've got a picture on the next slide where we'll explore that a little bit more. But as the electron moves closer to the nucleus, in terms of the energy level that it's in, the energy becomes lower, it becomes more negative. So here is sort of a plot of the energy levels in a hydrogen atom. And so the 0 is somewhere off the scale, right? 0 is somewhere up here in terms of the 0 of energy, where at that point we've removed the electron completely from the nucleus. And so this quantum number n, using this equation developed by Bohr, tells us the energy of the orbit, or as we'll come to call them, the orbital that the electron resides in. And so the line spectra is the result of electrons moving from higher energies to lower energy levels. And not only can atoms emit photons, they can also absorb photons. And so when we absorb a photon, the electron is going to move from one of the lower energy levels and be promoted into one of the higher energy levels. And when we have emission of a photon, the electrons are moving to lower energy levels. So again, when we absorb a photon, we're going from a lower energy level to a higher one. When an atom emits a photon, it's going from a higher energy orbital and dropping down into a lower one. Now, the energies of the of the orbits, or as we'll call them, the orbitals, is interesting, we're also really interested in what is the difference in energy between these different energy levels, because that tells us what is the energy of the photon that's going to be absorbed or emitted. So to do that, if we want to know the change in energy of the electron as it moves between these different energy levels, right, anytime we're looking for a change, we always do the final minus the initial. And so if we take the equation from the previous slide and do the final minus the initial, we can collect it into this new equation that will tell us the difference in energy between orbitals. And then when an electron makes a jump between these two different orbitals, we can calculate that the change in energy, and then the absolute value of that will be the energy of the photon. And the reason I say to take the absolute value is because in the case of absorption, the change in energy is going to be positive. The electron is increasing in energy, so delta E will be positive. When an electron is emitted, the electron is going from a higher energy to a lower energy, and so in that case, delta E is going to be negative. But the energy of the photon itself can't be positive, or I'm sorry, it can't be negative. And so in the case of emission, we'll want to take the absolute value of it. Okay, in a separate video, I have a quantitative example using the equation from the previous slide, where we'll use that to do some calculations on the energy of photons either being emitted or absorbed. But I also wanted to look at some qualitative questions. So I have some statements here, and I want us to indicate whether each statement is true or false. So in A, we're told that when an electron moves from n is equal to 2 to n is equal to 5, which I don't have, I'll draw in as n is equal to 5, it's saying when that transition happens, a photon is emitted. So for each of these, take a second to think about it, or pause the video, and then once you've made your prediction, go ahead and restart it. Okay, so for A, I think this statement is false, right? When I go from a lower energy level to a higher energy level, the electron is increasing in energy, and so therefore it's going to need to absorb energy. It's going to need to absorb a photon. So if I changed emitted to absorb, that would have been true, but as written, that statement is false. All right, the next statement says that the energy absorbed by an atom when the electron moves from n is equal to 1 to n is equal to 4, so that's true, we would have to absorb a photon to do that, but they're saying that energy is greater than the energy emitted when the electron moves from n is equal to 4 to n is equal to 1. And so that would be false, right? The difference in energy between n is equal to 4 and n is equal to 1 is constant, and so if I absorb the energy, when I go from 1 to 4, the exact same amount of energy is going to be emitted when the electron makes a transition in the other direction. So this statement would also be false. All right, so I don't know if I've used this term yet or not, but in part C it's talking about the ground state. So the ground state of any system is the lowest energy state. And so this is saying that the n is equal to 0 is the ground state of the hydrogen atom. And so that would also be false, right? Because the lowest energy level in the hydrogen atom is for n is equal to 1. So that would be false. If I changed that to a 1, then that would have been true. All right, so D says the wavelength of light emitted when an electron moves from n is equal to 5 to n is equal to 3. So let me draw that in. When we move from n is equal to 5 to n is equal to 3, is shorter than the wavelength when it moves from n is equal to 5 to n is equal to 4. All right, so I think this is going to take some evaluation here. So they're asking about the wavelength, right? And what this chart is telling me about is the energy. So when I go from n is equal to 5 to n is equal to 3, that requires more energy. When I go from n is equal to 5 to n is equal to 4, that requires less energy. And remember the relationship between wavelength and energy. So they're inversely proportional. So if it requires more energy to go from n is equal to 5 to n is equal to 3, then that's going to be a shorter wavelength, and that's going to be a longer wavelength. And so this says the wavelength of light emitted when an electron moves from n is equal to 5 to n is equal to 3 is shorter than the wavelength that moves from n is equal to 5 to n is equal to 4. So I think that statement is in fact true. Okay, and then the final statement, the frequency of light absorbed when an electron moves from n is equal to 1 to n is equal to 6. So now it's talking about we're going from 1 to 6, which I didn't have in here. We'll have n is equal to 6, is less than the frequency when it moves from n is equal to 1 to n is equal to 3. So again, the n is equal to 1 to n is equal to 6. So that's more energy for that transition. This transition is less energy. And now it's talking about the frequency. And so frequency and energy are directly proportional. So if it requires more energy, that's going to be a higher frequency. And less energy is going to be a lower frequency. So when this says that the frequency of light absorbed when an electron moves from n equal to 1 to n equals to 6, this is saying that this would be less frequency, so that would be false. Okay, so at least to our discussion to this point, all is well with the Bohr model. But it turns out there were some problems with it. And so in terms of predicting the energy levels, it only worked for the hydrogen atom. And it failed when it was used to try to predict the spectra of other atoms. We also now know that electrons do not move around the nucleus in circular orbits. So you'll often see a picture like this of an atom. Even in the crest of the School of Science and Technology here at GGC, we have this Bohr model, and that just drives me nuts because we've known for over 100 years that that is not the correct picture of an atom. And Bohr knew it too. Bohr helped develop the correct model of the atom, the quantum mechanical model for the atom. And so I'm sure if he was still with us today, he'd be really disappointed that 100 years later, they're still using his early incorrect model when he was one of the main contributors for determining what the correct model is. And so that's what we'll talk about in the next videos. So I have first, the very next video is a quantitative example using the equation to calculate the difference in energy levels and the frequencies and wavelengths of the emitted or absorbed photons. But then the video after that will get into what the correct model is for describing electrons in an atom.